Hello, in this video we're going to look at the Nobel Prize in Physics for the year 1908, awarded to Gabriel Lippmann for his method of reproducing color photographically based on the phenomenon of interference. First his work, coming from the Nobel Prize site directly. During the 19th century, methods were developed for producing black and white photographs with the help of light-sensitive silver halides. That is a chemical compound. In the 1890s, Gabriel Lippmann discovered a method for color photography based on interaction between light waves. Using a mirror, light was reflected through a photographic emulsion in which the interference phenomenon produces a number of blackened layers. The distance between the layers corresponds to a certain wavelength and can be transmuted into a color image. The method never came into widespread usage, but lived on as a physics experiment. Here you see the man at work in his laboratory at the Sorbonne University, that is in Paris. Here it is, Paris. Then some biographical information summarized by me, also from the Nobel Prize site. In 1873, he, that's Lippmann of course, worked with Kühne and Kirchhoff in Heidelberg and with Helmholtz in Berlin. Lippmann joined the Faculty of Science in Paris, and in 1878 and in 1883 was appointed professor of mathematical physics. 3 years later he became professor of experimental physics, studying Jamin, and he was appointed director of the research laboratory, which was subsequently transferred to the Sorbonne. He retained his position until his death. Lippmann, of original and independent mind, made valuable fundamental contributions to many different branches of physics, especially electricity, thermodynamics, optics and photochemistry. In Heidelberg he studied the relationships between electrical and capillary phenomena. This led to the development, among other instruments, of his extraordinarily sensitive capillary electrometer. Professor Lippmann had evolved the general theory of this process for the photographic reproduction of color in 1886, but the practical execution presented great difficulties. However, after years of patient and skillful experiment, he was able to communicate the process to the Academy of Science in 1891, although the photograph was somewhat defective due to the varying sensitivity of the photophatic film. In 1893 he was able to present photographs made by A and L Lumière, in which the colors were produced with perfect orthochromatism. He published a complete theory in 1894. In 1895 Lippmann evolved a method of eliminating the personal equation in the measurements of time using photographic registration, and he studied the erudition of irregularities of pendulum clocks, devising a method of comparing the times of oscillations of two pendulums of nearly equal period. He contributed to astronomy with this invention of the zoelostat, a device which immobilized the image of a star and its surrounding stars so that a photograph may be taken. This is from the Nobel Prize site. If you want to read complete biographical information, follow this link, type it over or Google it or something like that. Here you see the man at work at his laboratory. And again, then the award ceremony speech by Professor Lundberg. Even before 1849, when the art of photographic reproduction was discovered by the pioneers of science, Niepce, Daguerre, Talbot and others, the questions of means of rendering and of fixing colors on a photographic plate has loomed large. It looked as though the answer was at hand when Edmond Becquerel showed that a silver plate coated with a thin layer of silver chloride colored up under the action of light with a color corresponding to that of the light used. This observation led no further. Becquerel had no explanation for the origin of the colors, nor did he find a means of fixing them on the plate. They passed off rapidly, and so his method, being thus of no practical use, failed to win the attention it undoubtedly deserved. One explanation for the origin of Becquerel's colored images was given in 1868 by the German Wilhelm Zenker and then taken further by the Nobel Prize winner Lord Rayleigh. According to this explanation, the color phenomenon is due to standing light waves that by chemical action form grains of silver metal on the silver chloride. Color is an interferential phenomenon produced by the reflection of light on these silver layers. The phenomenon thus became of theoretical interest. If the truth of this theory could be shown, the work of Becquerel would afford further proof of the correctness of our concept of light considered as the result of vibratory movement, since one of the fundamental phenomena of vibratory movement, the standing wave, would thus be verified for light. It was, however, not until 1890 that Otto Wiener, by a particular fine experiment, furnished the conclusive evidence of the correctness of Zenker's theory. It is now possible to reproduce pictures in the more or less exact colors, but still not stable. Explanation had to be found for the origin of these pictures. It was still not time to talk of photographic reproduction of color objects and their fixation. This was the point reached when Professor Lippmann in 1891 communicated to the Paris Academy of Science his sensational work Color Photography. The main features of the Lippmann method are doubtless fairly well known. On plain glass, a layer sensitive to light is spread, consisting of gelatine emulsion, silver nitrate and potassium bromide. To this sensitive layer, a layer of mercury is applied, forming a mirror. This is exposed in the dark room in such a way that the glass side of the plate is turned towards the objective. During exposure, light has to pass through the glass first, then penetrate the imprint layer and encounter the reflecting surface of the mercury, which throws it back. These incident and reflected light rays form what are called standing waves, characterized by a series of maxima and minima of illumination, distant from each other by a half wavelength of the incident light. Once the plate is developed, fixed and dried by normal processes, there will be found in the layer of gelatine planes of reduced silver whose reciprocal distances depend on the wavelength, that is to say, on the color of the light which produced the image. Let us suppose that light falls on the normal way on a photographic plate disposed as we have described. The ray will be reflected by the different planes of silver, and following known laws of interference of light in thin lamina, the foil will appear colored, and colored with the same colors as the light that gave rise to the corresponding photographic print. The reproduction of colors is thus being carried out hereby the same way as in soap bubbles and thin lamina in general, with additional strengthening by the existence of successive planes. The effect of color in Lippmann's experiment does not therefore arise from pigment colors. We have to do with what are called virtual colors, interable in composition and bright for as long as the photographic plate is intact. Thus Lippmann's photographs show up favorably in comparison with later attempts of solving this problem of color reproduction. Lumiere's photographs, the so-called free color photographs obtained by using pigment colors, a delightful discovery which, owing to the simplicity of the operational method, has rightly won the measure of popularity. One glance at the illustrated work of our day, both in the domain of science and in art and industry, is enough to show the key position of photographic reproduction in present-day life. Lippmann's color photography mark a further step forward, which is of great importance. In the art of photography, since this method has been the first to give us the means of representing to posterity in unalterable picture form not only the shape of the object with its play of light and shade, but its colors as well. Those sustained efforts directed towards his end, and through his complete grasp of all resources that physics can offer, Professor Lippmann has created this elegant method of obtaining images which combines stability with colorific splendor. This achievement the Royal Academy of Science has considered worthy of the award of the Nobel Prize of Physics for the year 1908. This is the speech. Where you read it in its complete, you can follow this link. Here you see an illustration of some other work the good man did. He invented electrocapillary motor, for instance, and also the Lippmann electrometer. Maybe you're wondering, where are the photographs? Well, they will be in the next video on this subject, in which the Nobel Prize lecture of Gabriel Lippmann will be dealt with, and then that video will also contain some of the photographs he made. For now, thank you for watching, and maybe till next time.